Um, when you stand in your bathroom brushing your teeth, there's this, I don't know, this expectation of total, just boring safety.
Oh, absolutely. It's the definition of mundane, just a completely routine part of the morning for billions of people.
Right. You look at that tube of toothpaste, and it just represents basic everyday hygiene. It protects you. It's comforting.
Yeah, totally harmless, or so you'd think.
Exactly. But then you peel back the history, and you look into the actual chemistry of what is inside that tube, and that boring safety just completely shatters.
It really does. It's wild.
Because the fluoride protecting your teeth comes from an element so profoundly deadly, so violently reactive, that it actually blinded, maimed, and literally killed the early chemists who just tried to discover it.
Yeah, it's a pretty dark origin story.
It is. So today we are unraveling one of nature's greatest and honestly most terrifying paradoxes. We're doing a deep dive into some notes and excerpts from this fascinating document titled Fluorine, the Corrosive Catalyst of Modern Innovation.
It is a great source material, by the way.
Oh, it's incredible. Our mission for this deep dive is to figure out how fluorine, an element notorious for its extreme danger, has somehow become completely indispensable to modern civilization.
Right, because we're going to trace that path from a terrifying, untamable gas all the way to the modern infrastructure that you rely on every single day. I mean, the device you are using to listen to us right now.
Yeah, your phone or your laptop.
Exactly. The silicon chips, the battery, the screen coating, they literally would not exist without the very element that used to routinely blow up 19th century chemistry labs.
Which is just insane to think about. But okay, to understand how fluorine shapes our world today, we first have to look at the tragic, honestly explosive history of just trying to isolate the stuff.
Yeah, the early days were rough.
Rough is an understatement. In the 1800s, chemists knew there was an unknown element hiding in certain minerals, specifically this stuff called fluorspar. But trying to extract it was practically a death sentence.
It was. It earned this really dark reputation as chemistry's untamable element.
Yeah.
You had brilliant minds like Humphrey Davy and Carl Wilhelm Scheele,
Heavyweights of chemistry.
huge heavyweights, and they were attempting to isolate it. They would use electrolysis, or they'd mix fluorspar with sulfuric acid, which creates hydrofluoric acid gas. And when they inhaled it, or, when it even just touched their skin, the results were horrific.
Like severe poisoning, right?
Oh, severe poisoning, ruined lungs, temporary and permanent blindness. It was
Yeah.
brutal.
I mean, it wasn't just hard to find. It actively fought back against anyone who tried to pull it out of its natural state. And the reason for that struggle, based on the science notes here, is that fluorine is practically never found free in nature.
Exactly. It's never just hanging out on its own.
Right. You don't just stumble across a pocket of pure fluorine gas the way you might find, I don't know, a vein of gold or a pocket of oxygen. It bonds. And the chemical bonds it forms are some of the strongest in the universe.
So isolating it means you are forcing apart atoms that desperately, violently want to stay together. It took decades of failure and severe injuries before a French chemist named Henri Moissan finally cracked it in 1886.
And his process sounds more like bomb disposal than chemistry.
Oh, totally.
I mean, to get pure fluorine gas, Moissan had to cool his entire apparatus down to minus 50 degrees Celsius just to slow the reaction down. And he had to build his equipment out of platinum and iridium.
Which is incredibly expensive.
Yeah, he used those extremely rare metals just so the fluorine wouldn't immediately eat through the containment vessels the second it was created.
And even with those precautions, the pure fluorine still corroded his platinum equipment. I mean, he pulled it off, he won the Nobel Prize, but the process took a massive physical toll on his health.
It's just a perfect demonstration of how aggressive this element is. Which brings us to the mechanics of the element itself. Let's look at the science for a second. Atomic number 9, part of the halogen family on the periodic table.
Right next to chlorine and bromine.
Yeah. And if you do manage to get it alone, it takes the form of this pale yellow gas. Visually, it looks almost innocent.
But it is highly toxic and unbelievably corrosive. And to understand why it behaves this way, we have to look at the subatomic architecture.
Right, let's unpack that.
It comes down to a fundamental concept called electronegativity, which is basically a measure of how strongly an atom attracts electrons. Out of all the elements on the periodic table, fluorine has the absolute highest electronegativity.
Okay, let's visualize what that actually means in simple terms. I like to think of fluorine as a subatomic black hole for electrons. Or, like the ultimate electron thief at a subatomic party.
That's a great way to look at it.
Right. because it has 9 protons in its nucleus, and it has 7 electrons in its outer shell. And the rules of chemistry dictate that it desperately wants 8 electrons in that outer shell to become stable.
It just needs that one more.
It's just one. But because it is such a small atom, those 9 positive protons are incredibly close to the outer shell, exerting this massive localized gravitational pull. When pure fluorine gas shows up, it doesn't just casually ask a neighboring molecule to share an electron.
No, it's not polite at all.
Not at all. Its pull is so immense it violently rips the literal atomic structure of neighboring materials apart to get what it wants.
And that extreme localized pull is the actual engine of its reactivity. If pure fluorine gas contacts human skin or lungs, it immediately attacks the water molecules and the proteins in your cells.
Ugh, which sounds awful.
It is. It strips away their electrons, causing the cellular structure to physically collapse and burn, while simultaneously producing hydrofluoric acid directly inside the tissue.
Wow.
Yeah. It is a nightmare to store because it will strip electrons from the glass or the metal of almost any container you put it in.
So essentially eats the jar.
It eats the jar, the shelf the jar is sitting on, and
Huh.
eventually the building itself if you don't contain it in very specific pre-fluorinated metals like nickel.
Wait, how does nickel survive?
It forms a protective passivation layer, so it reacts a little bit and then forms a shield against further attack.
Okay, hold on though. I need to push back on the scale of this reactivity.
Yeah.
Because the notes talk about this, and you're saying it attacks basically anything to get that electron. But what about noble gases?
Yeah. The noble gas?
All right, because high school chemistry teaches us that gases like xenon, neon, and argon are completely inert. They are the untouchables of the periodic table because their outer electron shells are already full. They don't need or want to react with anything. Fluorine can't possibly breach a noble gas, can it?
Well, for a very long time, the entire global chemistry community believed exactly that.
Right.
Noble gases were thought to be completely unreactive by definition, but this is where fluorine breaks the standard rules of chemistry.
I knew it.
Yeah, its electronegativity is so overwhelming that under the right conditions, it can actually force a large noble gas like xenon to react.
Bullying a noble gas, I mean, that's insane.
It really is. Xenon is a big atom, meaning its outermost electrons are relatively far away from the pull of its own nucleus. So fluorine's pull is so strong, it actually distorts xenon's electron cloud, reaching in and dragging an electron away to form a compound called xenon difluoride.
That is mind-bending.
Yes.
It is a subatomic force so powerful it can basically force a noble gas into a chemical bond against its will.
Pretty much.
So if we are dealing with this rule-breaking, flesh-eating monster of a gas, how do we safely transition to the modern world? I mean, how do we go from an element that dissolves glass and forces xenon into submission to a paste that I casually brush onto my teeth before bed?
It's all about what happens after the theft. This is the central duality of fluorine. Free, pure fluorine gas. The unbound atom hunting for an electron is a terror.
Right.
But once it finds that electron, once it forms a bond with carbon or another element, it drops into a profoundly low energy state.
Oh, I see. It's like the black hole finally swallows enough mass and just completely stabilizes.
Exactly. The resulting chemical bond is incredibly strong and incredibly stable because fluorine holds onto its newly acquired electrons so tightly, the bond it forms is virtually indestructible.
Wow.
So the pure element is one of the most dangerous things on Earth. But the compounds it forms, the fluorides and fluoropolymers, are some of the safest, most chemically inert materials we have ever engineered.
That is such a wild paradox. We've basically hijacked that stability to armor plate our everyday lives. Take the toothpaste we started with. The enamel on your teeth is made of a mineral called hydroxyapatite, right?
Correct.
So when the bacteria in your mouth eat sugars, they produce acid, and that acid breaks down the enamel.
Yeah.
But when you introduce stable fluoride like stannous fluoride or sodium fluoride, it actually replaces the hydroxyl ion in your tooth enamel.
Yeah, it literally transforms the surface of your teeth into a new mineral called fluorapatite.
And fluorapatite is much harder and significantly more resistant to acid. You are essentially using the strength of the fluorine bond to create microscopic armor across the surface of your teeth, raising the threshold at which your enamel will dissolve.
Which is a modern medical miracle, but that same principle of indestructible shielding goes way beyond the bathroom sink. It scales up to massive industrial applications too.
Like what?
Think about a non-stick frying pan coated in PTFE, commonly known as Teflon.
Oh, sure. I have like 3 of those in my kitchen.
Most people do, and the mechanics of Teflon are a perfect example of this duality. Teflon is basically a long chain of carbon atoms completely surrounded by fluorine atoms.
Right.
And because those fluorine atoms are holding onto the carbon's electrons with an absolute death grip, they have absolutely no interest in reacting with anything
They're
else.
satisfied.
Right. The fluorine shell is so dense and stable that other molecules simply slide off it. That is why your scrambled eggs don't stick. The fluorine refuses to interact with the proteins in the food or even the soap you use to wash it.
It's an impenetrable chemical shield. And the notes say that same shielding is critical in medicine too, right?
Oh, massively. Pharmaceutical companies use carbon-fluorine bonds to protect life-saving drugs. When you take a medication like certain antidepressants, cholesterol-lowering drugs, or antibiotics, your liver's job is to metabolize it, right? To break it down and clear it from your system using specific enzymes.
Yeah, your liver is basically the body's bouncer.
Exactly. So by strategically replacing a hydrogen atom with a fluorine atom on a drug molecule, chemists can create a metabolic block. The liver's enzymes are designed to break carbon-hydrogen bonds, but they simply aren't strong enough to snap a carbon-fluorine bond.
Oh, wow. So it just bounces off.
It bounces right off. This prevents the drug from being broken down too quickly, allowing it to stay in the bloodstream longer and do its job effectively. In fact, about 20 to 30% of all modern pharmaceuticals contain fluorine for this exact reason.
That is incredible. So we have dental armor, non-stick coatings, and time-release medicine. But we also have to look at heavy industry. I mean, this element is a critical component in aluminum production and modern refrigerants.
Yes, and don't forget nuclear power. The most staggering industrial application has to be uranium enrichment.
Oh, wait, really? Fluorine is used in nuclear power.
You literally cannot have modern nuclear energy without fluorine. To fuel a nuclear reactor, you need a specific isotope of uranium, U-235. But in nature, U-235 is mixed in with a much larger amount of U-238.
You have to separate them.
Exactly. And to separate them, you have to turn the solid uranium into a gas and spin it in massive centrifuges. So the heavier U-238 moves to the outside and the lighter U-235 stays in the center.
But turning a heavy metal like uranium into a gas requires a very specific chemical partner, I imagine.
It does. You combine the raw uranium with pure fluorine to create a compound called uranium hexafluoride. It turns into a gas at relatively low temperatures. But here is the brilliant part. Fluorine only has one stable isotope in nature, fluorine-19.
Meaning every single atom of fluorine weighs exactly the same.
Yes, every single one. So when you attach 6 of them to a uranium atom, you know that any difference in the total weight of the gas molecule is entirely due to the uranium inside it.
Oh, I see. Because if you used a different element like chlorine, which has multiple isotopes of different weights,
The centrifuges wouldn't be able to accurately separate the uranium. It would be a mess. Fluorine provides the perfect, uniform baseline required for nuclear enrichment.
it is basically the hidden backbone of global infrastructure. But if you think its reach stops at nuclear power, we are missing the most critical part of this deep dive. Because fluorine is the silent architect of the digital age.
Oh, without a doubt.
If we suddenly lost access to fluorine today, the entire artificial intelligence revolution would stall instantly.
It all comes down to semiconductor fabrication. The chips that power AI hardware, our smartphones, the servers running the internet, they are built with microscopic precision. We are talking about carving transistors that are only a few nanometers wide.
Right, you can't just use a tiny saw for that.
No, you cannot do that with mechanical tools, and you can't even use standard chemicals. Manufacturers use a process called plasma etching, and the gases used to do that etching are highly dependent on fluorine.
Because you need something aggressive enough to bite into solid silicon with absolute atomic precision.
Inside a vacuum chamber, they turn fluorine gas into a plasma. Those charged fluorine ions basically act as microscopic chisels. When they hit the silicon wafer, they react with it to form silicon tetrafluoride, which is a gas.
So it just evaporates.
It just floats away, leaving a perfectly carved microscopic canyon in the silicon. Fluorine's extreme reactivity allows us to literally sculpt the architecture of the modern world at the atomic level. Without it, Moore's law collapses, and the high-performance computing required for AI simply isn't possible.
And its reach extends even further into the extremes of space exploration. Aerospace engineers rely heavily on the sheer stability of those fluoropolymers you mentioned earlier.
Oh, definitely. Out in space, you need materials that won't fail.
Right? Materials formulated with fluorine are used for rocket seals, fuel hoses, and advanced coatings that can survive the brutal, unforgiving vacuum of space. They resist the extreme heat of launch, the cryogenic cold of liquid oxygen, and the intensely corrosive nature of rocket fuels.
It's quite poetic, really. We take the most dangerous, aggressive element on Earth, we tame it into an indestructible bond, and then we use it to protect our most advanced technology in the harshest environments imaginable.
It is poetic.
Yeah.
But, and here's the sobering realization from the source material, there is a catch.
There always is.
The very thing that makes fluorine compounds so miraculously useful, the fact that the carbon-fluorine bond refuses to break down, is exactly what makes them an absolute environmental nightmare.
Yeah, this is the dark side of the fluorine paradox. When chemists synthesize these incredibly stable fluoropolymers and related chemicals for industry, they're introducing molecules that nature has never seen before.
Molecules that don't exist in the wild.
Right. Biological systems like bacteria, fungi, environmental enzymes, they evolved over billions of years to break down carbon-oxygen bonds and carbon-hydrogen bonds. They literally do not possess the biochemical tools, the molecular scissors, required to cleave a carbon-fluorine bond.
Which means when these chemicals enter the environment, they just don't degrade. We're talking about PFAS, right? Poly and polyfluoroalkyl substances, which are universally known as forever chemicals.
Yes. The same chemical armor that stops your eggs from sticking to a pan or protects a space shuttle valve doesn't just vanish when the product is thrown away or when industrial runoff hits a river.
They just stay there.
They persist in the environment for thousands of years. They leach into groundwater, they travel through the atmosphere, they enter the food chain, and ultimately they accumulate in the bloodstreams of human beings and wildlife worldwide.
Which is terrifying. The environmental and health impacts are severe. Based on the notes, we're dealing with industrial fluoride pollution, profound workplace exposure hazards for the people actually manufacturing these chemicals, and the reality that these synthetic molecules are linked to various health risks precisely because the human body cannot metabolize them.
It is the ultimate trade-off. We desperately need the unique properties of this element to manufacture the infrastructure of the modern world, but we fundamentally lack the ability to safely dispose of the synthetic compounds we create from it.
It's like we summoned a genie that performs absolute miracles for our technology, but refuses to ever leave the room.
That's a really good way to put it. And it creates an immense regulatory challenge. I mean, how do governments ban or restrict a class of chemicals that are polluting the global water supply when those exact same chemical properties are the foundational material for life-saving medical devices, clean energy infrastructure, and the semiconductor industry?
You just can't easily untangle the hazard from the utility.
You really can't.
And looking at the trajectory of technology, we aren't backing away from fluorine. Despite all the pollution challenges and the bans on specific types of PFAS, our reliance on the element itself is actually accelerating. The horizon technologies that will define the next 50 years are completely dependent on it.
Absolutely. The transition to green energy, for example, requires massive advancements in battery technology. Solid-state batteries and next-generation lithium-ion architectures rely heavily on fluorinated compounds for their electrolytes and binders to prevent degradation and thermal runaway.
We are also looking at the materials necessary for quantum computing hardware, next-generation deep space habitats, and even smaller, hotter, faster semiconductors. As our technology scales down to the sub-nanometer level and operates at higher extremes of temperature and energy, we need materials that can withstand those environments.
And nothing in the universe withstands extremes quite like a fluorine bond.
So summarizing the sources, fluorine truly is nature's greatest paradox. Left in its natural unbound state or managed carelessly in industrial byproducts, it is an intense existential hazard.
But engineered with precision, it is the silent catalyst of human progress. It gives us cavity-free teeth, targeted pharmaceuticals, clean energy, and the computing power that basically runs the modern world.
It has been a wild journey on this deep dive. From an untamable violent gas that terrified and blinded 19th century chemists to the indestructible partner of the digital age.
It's an incredible story.
It really is. And that brings us to a final thought for you to chew on today. We have built our entire futuristic infrastructure, from the artificial intelligence brains dreaming up new innovations to the deep space rockets pushing us to other planets, on an element that is notoriously dangerous to handle and practically immortal once it is manufactured.
Yeah, it doesn't go away.
It doesn't. So if our demand for AI, green energy, and advanced tech continues to skyrocket, are we quietly building a utopian high-tech future on a chemical foundation that we might ultimately lose the ability to control or clean up?
That tension between innovation and permanence is really the ultimate question of the fluorine age.
It really is. Thank you for joining us on this deep dive. Keep looking closely at the everyday objects around you, even something as simple as your toothpaste, and keep asking big questions about the tiny atoms shaping your world. We'll catch you next time.